Okay, let's start proving Ito formula. So we look at f of bt minus f of 0, and we need to show that this is going to be equal to the integral from 0 to t of f prime bs dbs plus 1/2 of the integral from 0 to t of f second of bs ds. Okay, so we need to relate f to its derivative, and to start with, what we're going to do is we're going to use a telescoping sum to rewrite f of bt minus f of b0 as the sum from j equal 1 to n of f of bj over n minus f of bj minus 1 over n. Right? The idea is that we want to look at small enough time interval to be able to approximate the difference of the function at two different points by its derivative. Now, this sort of approximation, of course, are captured by Taylor's formula, which we recall here, that tells us that for every x and y in R, because my function f is C2, I have f of y minus f of x approximated to first order by y minus x times f prime of x, and just this approximation would be good enough for proving the standard fundamental theorem of calculus in deterministic calculus. But because the quadratic variation is non-zero here and is related to the second derivative of f, I'm not going to be able to just use a first order Taylor formula. So I'm going to use a second order Taylor formula in proving the stochastic version of the fundamental theorem of calculus. Right? That has to do with the fact that the quadratic variation of the Brownian scales linearly in time. So it's really of the same sort of size as this first order approximation. But then you still have higher order term, of course, unless you have a polynomial of degree 2. You have higher order terms here involving third derivative and so on and so forth. And these terms really are just going to be error terms. We're going to show that as n goes to infinity, these things go to 0 in the appropriate topology. So we'll get back to them a bit later. Now, applying Taylor formula and my telescoping sum, what I have is f of bt minus f of b0 is equal to what? Well, it's equal to the sum j equal 1 to n of f prime of bj minus 1 of n times bjn minus bj minus 1 of n. Very good. Plus, what is it? I forgot the 1/2 in my Taylor formula. It's really where this 1/2 comes from, and then I get 1/2 of the sum j equal 1 to n of f second of bj minus 1n times bjn minus bj minus 1n squared, and then I have a error term that I'm going to call Sn. Right, so Sn is going to be the sum j equal 1 to n of the r of bjn comma bj minus 1n. Now, this is looking good because what we have here is really an approximation of the integral of f prime bs dbs. This is the theorem about Riemann sum approximation of the Ito integral of a continuous function of the Brownian that we've seen in a couple of videos ago. So this theorem is going to be extremely helpful as promised, because it's going to tell us that this term converges to what it should converge to. What we have here, okay, this doesn't quite look like something that converges with that. So let's compensate for that. So we have this first term, which should be giving the integral, which will give the integral of f prime bs dbs in the Ito sense. And then we want a term here with a j over n minus j minus 1 over n. And this term, by the way the Riemann integral is constructed, will converge to the integral of f second bs ds. Now I've added that term, I need to subtract it, so I'm going to have a term that is j equal 1 to n f second of bj minus 1n bj over n minus bj minus 1 over n squared minus j over n minus j minus 1 over n. And now this term is the terms which we will have to prove go to 0. And as you can tell, this is related to the quadratic variations of the process, right? Which will be studying the limit of sums of these objects and showing that they behave like the sum of those objects. So the difference really should be going to 0. Right, so okay, so what have we got? We have that this term converge to the first term by the theorem about Riemann sum approximation of E2 integral. This term converge to this term just by construction of the Riemann integral, and we have to show that this error term and this error term go to 0. Okay, so this is looking good. What we have here is a term that converges in probability to the integral of f prime bs dbs. That's thanks to this result about Riemann sum approximations of E2 integral. The second term here converges almost surely to the integral of f second bs ds. That's because this is defined as a Riemann integral, so for every fixed value of omega, or almost every value of omega for which the Brownian is continuous, then you're integrating a continuous function, f second of bs of omega, and you know by the theory of Riemann integrals that this is an approximation. So we have a probable convergence in probability of this to the first term, convergence almost surely of this to the second term, and now all we have to do really is to prove that these two error terms, this one coming from quadratic variation and this one coming from higher order term in the Taylor formula, do go to 0 in appropriate topologies. So let's start with that first one, the one that comes from quadratic variation theory. All right, so here's the term, and I'm going to define, give it a name, let's call it Rn. Rn is 1/2 sum j equal 1 to n f second bj minus 1. Really, I'm showing it's going to 0 anyway, so forget the 1/2 times bj over n minus bj minus 1 over n squared minus this j over n minus j minus 1 over n, which is really just 1 over n. Okay, this is Rn, and so I'm going to claim here that Rn goes to 0 actually in L2 norm, as n goes to infinity. Right, so let's prove that. So to do that, we use the usual trick of expanding the sum, the double sum, and using some orthogonality. So let's call them j and k be two numbers between 1 and n, and let's assume that j is greater than k. And then let's have a look at the expectation of f second of bj minus 1n, f second bk minus 1n times bjn minus bj minus 1n squared minus 1 upon n times bk over n minus bk minus 1 over n minus 1 upon n. This is squared. Right, so we're looking at this expectation, and as always, the expectation is equal to the expectation of a conditional expectation, irrespective on what I'm conditioning upon. So I'm going to condition on fj minus 1 over n. That's right, such that most terms will be measurable with respect to fj minus 1 over n, but not all of them. So I take the expectation of the conditional expectation of this gigantic thing, right, and I'm conditioning on fj minus 1 over n. Now, what does that give me? So remember, I have a continuous function of the Brownian with f second, and my j is greater than k. So a lot of these things, this is fj minus 1 measurable, this is fj minus 1 measurable, this is fj minus 1 measurable. Now, this isn't, because this involved bj over n, which is not fj minus 1 measurable, minus 1 here. But take out what is known in the conditional expectation, and you get that this is the same as the expectation of f second bj minus 1 over n f second bk minus 1 over n times bk over n minus bk minus 1 over n squared minus 1 upon n, and then times the conditional expectation of bj upon n minus bj minus 1 upon n squared given fj minus 1 upon n, and then that's minus 1 upon n. Right. 1 upon n, of course, is just a number. It's certainly fj minus 1 upon n measurable. Okay, now here, this is the only term that for which I cannot use take at what is known in the conditional expectation, because this is not j minus 1 upon n measurable, but it's not j minus 1 upon n measurable, it's the absolute opposite. It is independent of fj minus 1, because the increments of the Brownians are independent. And so what we have, right, so this increment is independent of all the variables that generate this sigma algebra. So it's independent of this sigma algebra. So the conditional expectation in that case, let's not rewrite another line, let's just rewrite it like that. This conditional expectation has to be equal to the actual expectation by independence. Right? And what is this expectation? Well, it is 1 upon n. So it exactly compensates this term here. And what we have here is 0. So in this double sum, and if I expand the square of Rn into a double sum, all the cross terms disappear by this orthogonality argument using the properties of the increment of the Brownian that we've seen quite a few times in this course. So what does that tell me? That tells me that the expectation of Rn squared is really the sum, j equal 1 to n, a single sum of the expectation of f second of bj minus 1 upon n squared times bj upon n minus bj minus 1 upon n squared minus 1 upon n, and then square this. So I want to estimate that. Now, really, I don't know much about this term here. So I'd like to get rid of that in all of my computations. I'd like to be able to control that by, let's say, the sup norm of f second. Now I know f second is continuous, but it's a function on all of R, so a continuous function on all of R doesn't necessarily have to be bounded. So we're going to make an assumption here. We're going to assume that f, and therefore f second, is compactly supported. It's 0. Let's write it even like that. We're going to assume that f of x is equal to 0 for all x not in the interval minus mm. So for some m in R or in n even. Okay, so let's put a massive box around that, because this is an assumption we are making. So if we can't remove that assumption eventually, then we would prove the ethos formula only under this extra assumption of compact support. But that's not going to be a problem. We're going to first assume that, prove our theorem, and then shows that if the theorem does hold for function that satisfy this assumption in the red box, the compact support assumption, then it has to hold for all C2 functions. So we can remove that assumption a posteriori. But assuming that we have that f second, the sup norm of f second for x in R is finite, right? Because the function f second is 0 outside of the compact set minus mm, and continuous function on a compact set have to be bounded. So what we get then is that the expectation of Rn squared is smaller than this sup norm. So we usually denote that, as we've seen before, by f second infinity. And so we get that this is smaller than f second infinity times the sum j equal to 1 to n of the expectation of bj upon n minus bj minus 1 upon n squared minus 1 upon n, and then square that. Okay, but that is something we can just compute, right? In fact, we've computed that before. So this is smaller than f second infinity, sum j equal 1 to n, and then you expand that squared, you get the expectation of the increment to the fourth, and that gives you a 3 upon n squared. You get the cross term, that gives you a minus 2 upon n squared, and then you get plus 1 upon n squared. Point being, and then you sum that, j equal 1 to n. So this entire thing is equal to f second infinity times 2 upon n squared times n, so times 2, and divided by n. And now this certainly goes to 0 as n goes to infinity. So under this extra compactly supported assumption that I've put in the red box, I can show that the error term Rn coming from the quadratic variation actually goes to 0 in L2 norm. Right. Now we'll need to remember that we need to remove the compact support assumption, but now we are left with one last term that needs to go to 0, which is the term coming from the higher order derivatives in the Taylor formula. Okay, so let us look at the term Sn, which is the sum j equal 1 to n of the little r of bj upon n, bj minus 1 upon n, where this little r is the rest in Taylor formula. So this is really equal to f of y minus f of x minus y minus x times f prime of x minus y minus x squared divided by 2 times f second of x. So this is a compactly supported, uniformly continuous function in x and y. So what we have is that we have that r of xy is equal to y minus x squared times hxy. Right, that's the general theory of rest error terms in Taylor formula. You can write that as integral, and you can factor out y minus x squared out of that at least. And what you have here is still going to be a uniformly continuous compactly supported function. Well, it's going to be a continuous compactly supported function, and compactly supported functions that are continuous are automatically uniformly continuous. So what we have is we have that h is such that, well, it's bounded and it's uniformly continuous. So that is to say that for every epsilon there exists a delta such that for all x, y, x tilde, y tilde in R, if the vector in R2 xy is close enough to x tilde y tilde, that's in the norm of R2, then fh, of xy minus h of x tilde y tilde has to be smaller than epsilon. So we're going to exploit that, and we're going to show convergence of Sn in L1 norm. So let's try to compute that. Well, what do we get? We get the, this is smaller than the sum, j equal 1 to n, and the expectation of bj upon n minus bj minus 1 upon n squared times h of bj upon n minus bj minus 1 upon n. And then I could apply Cauchy-Schwarz to this and get that this is smaller than sum j equal 1 to n of the fourth moment of increments of my Brownian raised to the power of 1/2 times the expectation, that's a comma, of h bj upon n, bj minus 1 upon n to the power 2 raised to the power 1/2. And now the fourth moment of my Brownian, I know what that is. That's 3 upon n squared. So this entire thing is equal to square root of 3 divided by n times the sum j equal 1 to n of this expectation of h of bjn comma bj minus 1n squared, and then you raise that to the 1/2. So it's great. I have this 1 upon n here that's going to help the convergence, but I have to show that this remains uniformly bounded in n. And that's where you use the property of h. H is bounded and it's also uniformly continuous. So you can look at two sets here and you can say, well, you can say that there are two possibilities. Either bj upon n, comma, bj minus 1 upon n is close to 0, or it's not. So if it is close to 0 by uniform continuity, I know that bj minus 1 upon n is smaller than epsilon, right? So I can have an epsilon square on the set of all those omegas in capital Omega for which bj upon n is close to bj minus 1 upon n. And then I have the set, so let's rewrite it as an integral. I have the integral of omega on the set where bj upon n minus bj minus 1 upon n is greater than delta. Right, and then I'm integrating my h, bj upon n of omega, bj minus 1 upon n of omega squared on that set. And then this is raised to the power 1/2. Okay, I forgot the power 1/2, so my epsilon square is really just an I should keep it as epsilon square, and the 1/2 is outside here. Right. So now here on the second term where bj is not close to bj minus 1, so I cannot use the fact that h of this is close to 0 in any way. So I'm just going to use the fact that it's bounded. So what I've got here is sum j equal 1 to n of epsilon squared plus the sup norm of h squared times the probability that bj upon n minus bj minus 1 upon n is greater than delta. And then all of that is raised to the power 1/2. But now this is smaller than square root of 3 upon n, sum j equal to 1 to n, epsilon squared plus sup norm of h, and then let's just control that by delta square expectation of bj upon n minus bj minus 1 upon n squared. Okay, and then raise that to the power 1/2. Okay, so what do we get now? We get that this is smaller than square root of 3 upon n, sum j equal 1 to n of epsilon squared plus h infinity squared divided by delta square times 1 upon n. And then all of that is raised to the power 1/2. Okay, but now this is a constant, so you can, sorry, the square root doesn't go all the way to the bottom, of course, only on the square root of 3. That's extremely important to have a 1 upon n here. This quantity that I'm summing is no independent of j, so I have n terms. I can get rid of this sum and get rid of this 1 upon n to control for the sum. So I've got square root of 3 times epsilon square plus this quantity. Now send n to infinity. As n goes to infinity, this goes to square root of 3 times epsilon. But of course, that is true for every epsilon. So we have that as I send then my epsilon to 0, then I get that expectation of Sn, the limit of that, or the limit sup of that to make sure it exists, is equal to 0. Okay, So what have we got? We've got convergence in L1 norm of Sn, convergence in L2 norm of Rn, convergence in probability of the term with f prime bs, and convergence almost surely of the term with f second bs. And all of that under the extra assumption that our function is compactly supported. So let's put all of these things together to conclude the proof. Okay, so first of all, from the convergence in probability, passing to a subsequence, I have almost sure convergence. Then for the f second term, I already have almost sure convergence. For the L2 convergence, again passing to a subsequence, I have almost sure convergence. And for the L1 convergence of this term, again passing to a subsequence, I have almost sure convergence. So taking a subsequence, passing to a subsequence nk, we have that, okay, we have that f of bt minus f of 0 when I take the limit from that subsequence. So if that's for every t in 0, 1, there exists a set omega t in sigma that has probability 0, such that for every omega not in omega t, f of bt of omega minus f of 0 is equal to the integral from 0 to t of f prime of bs dbs, that gives me a random variable, at omega plus 1/2 of the integral from 0 to t of f second of bs of omega ds. Right? That's what we got from all of the reasoning we've done so far, passing to a subsequence. So that's our Ito formula, but it's not almost sure quite yet. It's for every t there exists a set of measure 0. But now we use our classic continuity trick. We know that all of these processes are by definition continuous processes, and the Ito integral in particular is the unique continuous process that matches this value. So what we then get is that there exists a set E in sigma that has probability 0, such that for every omega not in E and for every t in 0, 1 intersected Q, f of, well, let's rewrite that like this. This is for 1 holds. Okay, and so by continuity, for every t in 0, 1, f of bt minus f of 0 is this integral almost surely, which is our Ito formula, but assuming that f is compactly supported. Right, so the last thing we need to do is to remove this compact support assumption. Let's do that now. Okay, so assume that f is not compactly supported. So you just take a general f in C2, you take an m, a natural number, and you define fmx equal to fx if x is between minus m and 0 otherwise. Now, your fm is compactly supported, so we have proven Ito formula for fm, and we just need to show that we can send capital M to infinity to get Ito formula for f. So we also define a family of stopping time. We define tau m to be this infimum of tau greater than 0, such that Vt is greater than m. Right, and what we have is that we have that f prime of Bs is equal to f prime m of Bs whenever s is below the stopping time. So this is, at a point omega, for every omega in omega, and for every s in 0, 1, such that s is smaller than tau m of omega. If s is smaller than tau m of omega, it means your bs of omega is smaller than m, so there's no difference between f prime and fm prime, because f and fm match on that set minus mm. Okay, but now, by the uniqueness theorem for the Ito integral, when you stop processes, what do we get? We get that the integral of f prime bs dbs from 0 to t has to be equal to the integral from 0 to t of f prime m bs dbs if t is smaller than tau m. So this is if you want at some point omega, if t is smaller than tau m of omega. So what have we got? We've got that if t is smaller than tau m of omega, then f of bt minus f of 0, well, it's f of fm bt minus fm of 0. And by the Ito formula for the compactly supported case, we get that this is equal to the integral from 0 to t of fm prime bs dbs plus 1/2 of the integral from 0 to t of f second m bs dbs. But we've just seen by uniqueness that this is the same as the integral of f prime bs dbs, and of course f second and f second bs and f second mbs, again, if t is smaller than tm, has to be the same. So this is f second bs, sorry, that's not dbs here, that's ds. So I don't use the uniqueness of the Ito integral, I just use the pathwise definition of the the Riemann integral. So I have my Ito formula now under this extra assumption that t is smaller than tm of omega. Right, but notice that tm, as m goes to infinity, the probability, right, that tm goes to infinity is 1, or put it in a different way, the probability that tm is 1, and I take the union over all m in n, is 1. So you give me any t by picking almost any omega, by picking m large enough, I have t smaller than tm of omega. So for every t in 0, 1, and so I should have said there exists a set E in sigma, which is probability 0, such that for all t in 0, 1, and for all omega not in E, there exists an m in n such that t is smaller than tm of omega. And therefore, there exists an E in sigma, which has probability 0, such that for all t in 0, 1, and for all omega not in E, f of bt minus f of 0 is equal to the integral of f prime bs dbs plus 1/2 integral of f second bs ds. Just pick your m sufficiently large to guarantee this, such that this formula holds. And that is literally Ito formula, almost surely. And that concludes the proof.